Hi guys, good morning everyone. This is Aditya Soni and we are back with our series on Advanced Linear Algebra. In previous videos we have done two important theorems which states that if V is any vector belongs to a vector space V, then the matrix representation of V with respect to standard basis beta is equals to Q times of V beta dash, that is Q into the matrix representation of V with respect to beta dash. And the other theorem that the matrix representation of the transformation with respect to beta dash is equals to Q inverse of T beta into Q. Okay, so further we did an example, and lastly we did the derivation of the reflection operator about the line y equal to mx. So from today's class we'll begin our example 3 and the later sections of the last part of our first section, that is section 2.5. So we would be doing this corollary example and the last example number 4. This all will cover in the today's class. So the example 3 talks about a transformation T that is defined from the vector space R square to R square, that is a linear transformation and is completely determined by the value in its basis. Fine. So it is given that it is a transformation about y equal to 2x, and this one is the perpendicular line. So for all points that lie on this line, it will map, the transformation will map them to the same point, and for all points that lie on the orthogonal complement, it will map to the negative component, as it says here, that is T of 1 1 is what? 1 is the point that lies on the line y equal to 2x. 1 2, I said 1 2, so T of 1 2 will go to 1 2, and it says that T of minus 2 1 goes to minus of minus 2 1, that is 2 minus 1. Fine. So this is a reflection operator about line y equal to 2x. We are given that beta dash is 1 2 minus 2 1. It is an ordered basis of R square, obviously. Both of them, they are Li and the order is 2. So we take the matrix representation of T beta dash. Fine. How to find out the matrix representation? You all know it. First of all, we need to operate the transformation on all the basis vector, and then the transformational image is written as the linear combination of each of the basis vector. Then the linear combination is arranged vertically, that is, this is for T of 1 2 and this is for T of minus 2 1, right? This is about T beta dash. Further, if beta equal to E1 E2, what is E1 E2? You guys all might be knowing. E1 E2 I told you in the very first class. E1 E2 are the standard basis if E1 is the 1 0 and E2 is 0 1. Fine. So E1 E2 is 1 0 0 1. So this is the ordered basis of R square, and if Q is the change of coordinate matrix that changes beta dash coordinate into beta, then how to obtain it? How to obtain the matrix Q, the change of coordinate matrix that changes beta dash into beta coordinates? So in order to find this matrix, I'll need to write the vectors of beta dash as linear combination of beta, and the linear coefficient will be arranged vertically. Fine. That is how we can do it. 1 2 is 1 times of E1, 2 times of E2. Minus 2 1 is minus 2 times of E1 and 1 time of E2. When you arrange it, you will be able to attain the Q matrix. Further, iska inverse, we can also find the inverse of this matrix. So Q inverse is what? Inverse of any matrix is defined to be 1 by determinant of A into adjoint of A. So for a 2 cross 2 matrix, the adjoint can be easily calculated. We need to interchange these two quantities and change the sign of these two quantities. So this is positive 2, this is negative 2, and both of them, they are same. When they interchange, they remain the same. So fine. Now we'll find the T with respect to beta. So how to find T beta? T beta, I have the formula. T beta dash is equals to Q inverse of T beta Q. I have T beta dash, I have Q inverse T beta Q. So when you multiply it, what I do? I pre-multiply by Q and post-multiply by Q inverse. Then I'll get, what I'll get? Q T beta dash Q inverse, it is equals to T beta. Fine. This is how what we have done here only. So T beta will be Q T beta dash Q inverse. You multiply it and obtain the T beta matrix. Okay. Fine. So we had evaluated this matrix T beta, that is 1 by 5 times of minus 3, 4, 4 and 3. Now since beta is the standard basis of what? The vector obviously. So standard basis, therefore T, the matrix, the transformation T will be the left multiplication by T beta. So how to obtain the transformation? For transformation that is acting on any kind of vector, say AB, that will be 1 by 5 minus 3, 4, 3 and AB. That is, I can also write it as matrix representation of T beta into AB. Okay, so that's how we have evaluated the transformation. This example taught us how to find the exact transformation if we're given the transformational images, basically transformational images on the basis vector. So using those images, we had first calculated the T beta dash and further we calculated the T beta using the formula we had, and using the T beta we evaluated our transformation. I hope this example would be clear. Okay, so let's begin with this corollary. It says that let A be a matrix over the field F of order n cross n. Let gamma be the standard ordered basis of Fn. Then the matrix representation of LA with respect to gamma equals to Q inverse AQ, where Q is the n cross n matrix whose jth column is the jth vector of gamma. So this corollary tells us to find out the matrix Q. Another method, this corollary explains the another method to find the matrix Q. Fine. So if we are given any matrix, then we can find out the matrix representation of LA. LA is what? It is a left regular multiplication operator. So let us first define the operator LA. Okay. If A is an n cross n matrix over the field F, then we can define LA from Fn to Fn, by LA of X. It is LA of X is AX for all X belongs to Fn. So if A is a matrix, a square matrix of order n over the field F, then we can define the operator LA, and it is basically termed as the left regular multiplication operator. The left regular multiplication operator. Since the A matrix was n cross n, then I defined it this way. The other way I can also define it to be Fn to Fm. But how to define it? Let me explain. Fn to Fm, that is also defined a similar way. LA of X is AX, where the order of AX is m cross 1, and the order of X is n cross 1. So Fn, the Fn vector goes to Fm vector. That's how it is defined. So let us see how this works. So if X is n cross 1, A is m cross n, then I already told you that for the multiplication for two matrices of different order exists if and only if the column of the first matrix equals to the row of the second matrix, and the order of the resultant product is the row of the first matrix and the column of the second matrix. This one is the order. I told you previously in the very first class while telling the basics of the linear algebra. So while multiplying it, we keep this thing in mind when the order of the matrix is different. So m cross 1 is the order. That's how the order comes, and since n and n are same, that's why we can define it. Okay, if the order is order of the matrix A is m cross n, that is the matrix is not square, then we define the left regular multiplication operator like this, and if it is a square matrix, then we define it from Fn to Fn. Okay, this is about the left regular multiplication operator. Okay, so the proof to this corollary was left as an exercise. I have this proof. The proof is very simple. Let's study it in detail. So we are assuming that beta be the standard basis E1, E2, En for Fn, and I am taking the gamma to be the basis, say V1, V2 and so on up to Vn. This is also an ordered basis. Okay, so V1, V2 and so on up to Vn, where V1 would be some like V11, V12, V1n and so on. V2 would be another column vector, V21, V22, V2n. Fine. So that's how we are defining. We are taking the basis beta and gamma. So if I define the left regular multiplication operator LA from Fn to Fn, then LA of x is Ax. That's how I defined it previously, that LA of x is Ax. It can be easily shown that the matrix representation of LA with respect to beta is A. If Q dash is the change of coordinate matrix beta dash into beta, so we first write the element of beta dash as the linear coefficient, because what I need to find out? I need to find out the matrix Q dash that changes beta dash to beta coordinates. So for the obtaining the matrix Q dash, I have the principle of obtaining the Q matrix, and that is how I represent the basis vector of beta dash as the linear combination of beta. Okay, fine. Now what is beta dash? Beta dash is gamma. I want to represent beta and gamma same. It is equals to gamma only. Okay? So V1, V2 and so on up to Vn can be written as the linear combination of E1, E2, En. V1 would be V11, V12, V1n. V2 would be V21, V22, V2n. Vn would be Vn1, Vn2, Vnn. When written as a linear combination, it can be written like this. Further, while obtaining the Q matrix, I need to arrange it this way. So V11, V12, V1n goes like this. V21, V22, V2n comes like this. Vn1, Vn2, Vnn comes like this. This is the Q dash matrix. And what does it do? What does it do? It does the change of coordinates from beta dash to beta coordinates. Fine. So this is the matrix Q dash, and I am taking it to be equal to Q only for simplicity in the calculations, for simplicity in the presentation. Now if I take LA with respect to gamma or say beta dash, whatever, because previously I defined gamma, and while taking the change of coordinates I had taken the beta dash, but beta dash and gamma are same in our proof. Okay, so LA with respect to gamma is what? That is Q inverse LA beta Q. What result we have used here? The result is this one. The matrix representation of a transformation with respect to beta dash is equals to Q inverse times of matrix representation of the transformation with respect to beta into Q, where Q is the coordinate change from beta dash to beta. That is why LA beta dash or LA gamma is equals to Q inverse LA beta Q. So what is LA beta? LA beta is A. That's how we obtained our proof. This LA with respect to gamma or LA with respect to beta dash is what? That is Q inverse A Q. I hope the proof is clear to all. Let's begin with example number 4. It has given to us a matrix of order 3. The matrix A is 2, 1, 0, 1, 1, 3, 0, minus 1, 0. And we are given a basis gamma. Why I am saying it is a basis for F3? It is a basis for F3 since the vectors are Li. Moreover, the order is 3. So it forms the basis for F3. Okay, so if A is a matrix of the field F3, then I need to find out the matrix representation of LA with respect to this matrix gamma. So how I define LA? LA is defined from Fn to Fn, and in particular it is F3 to F3. Why F3? Because the order of the order of A is 3. So it is LA is F3 to F3. So how it is defined? LA takes the vector X to AX. So if I go by the conventional method of finding the matrix representation, it may be tedious, it may be done. It may be done easily also, but I will use the previous corollary that we have recently studied. The corollary says that if A is a matrix of order n cross n, then gamma is the ordered basis of Fn. Then LA with respect to gamma is Q inverse AQ, where Q is n cross n matrix that changes beta dash to beta coordinates. Or moreover, the jth column in the matrix Q is the jth vector in the basis. So the very important term herein, let me show you the text. The very important term herein is that how to obtain the matrix Q. It gives us another method. If we are given exactly the basis gamma, then we can find out the matrix Q by putting the jth vector of the basis as the jth column in the matrix. So first vector in the basis will be the first vector in the matrix. Second vector, second column. Third vector, third column in the matrix. So this is the matrix Q. So further we find the Q inverse. How to find the Q inverse? 1 by determinant into adjoint. So 1 by determinant of Q into adjoint of Q. What will be the determinant? Determinant, this is a diagonal matrix. Simply we multiply it 1, 1 and minus 1. So determinant is 1 by minus 1 into adjoint. So adjoint. Okay, so determinant I think we all can calculate. It is A11, A12, A13, A21, A22, A23, A31, A32, A33. That is A11, A12 and so on. And what is this? This is the cofactor. That is minus 1 raised to power may I plus j into the minor mij. And the minor is this matrix. If I take ij, so you can calculate it now. 1, 1. The first row and the first column is eliminated. The remaining term is taken and we take the determinant. That is the minor. Fine. So that's how we evaluate the cofactor. Further, LA gamma we can find out by multiplying the matrices. That is the Q inverse AQ. So you multiply it and you will be able to obtain the result. It is plus 1. So this is the Q inverse matrix. This is the Q matrix, and LA gamma, when you multiply it, you can get the result. Fine. So this theorem, this example tells us if we are given exclusively, we are given the basis. We are given standard basis of Fn and a matrix of order n cross n, then we can find the matrix representation of the operator, left regular multiplication operator, with respect to the standard basis, maybe the ordered basis, more particularly I should say the ordered basis gamma. Fine. Now we have an important definition. The definition says when the two matrices are similar. Okay, so two matrices A belonging to the matrix M n cross n over the field F, we say that the matrix B and A are similar, because the relation of similarity is an equivalence relation, right? So A and B are said to be similar matrices if there exists an invertible matrix Q, if there exists an invertible matrix Q such that B can be obtained by A, B is equals to Q inverse AQ. Okay, so in some context it might also be mentioned that the matrix Q has to be non-singular. So the relation of non-singularity and the invertibility may be understood by the definition of invertibility and the non-singularity only. When the matrices are said to be invertible, invertible implies the 1 by determinant of A into adjoint of A. This is the property, this is the definition of invertible matrix and inverse of a matrix. And for the non-singular matrix, a matrix is non-singular if the determinant is non-zero. So if the determinant is non-zero, then only I can say the denominator here is defined and the inverse is defined. So for the inverse to be defined, the matrix has to be non-singular. So it is just equivalent condition if I say the matrix is Q is invertible or it is non-singular. Fine. So now we study some important remarks over here, and the remarks are here. As I told you just now, the relation of similarity is an equivalence relation, so we need only say that the matrix are A and B are similar. Fine. Now in this terminology, we can restate the theorem 2.23. Which theorem? We have just studied, we have just used it, this theorem, that T beta dash equals to Q inverse of T beta Q, theorem 2.23. I can also say that the matrix representation of operator T with respect to beta and the matrix representation of operator T with respect to other ordered basis beta dash of the field of the vector space, because transformation vector space to vector space it is defined, na? That is why. So beta dash and beta, both of them, these matrices are similar. Fine. So this is the restatement of the previous theorem that we had already proved. So this is, let T is a linear operator on finite dimensional vector space V, and if beta and beta dash are any ordered basis for V, the vector space V, then the matrices T beta dash and T beta are similar, or T beta dash is similar to T beta, or T beta is similar to T beta dash, because it is equivalence relation. Then this theorem may also be generalized for two different vector spaces and their respective different bases. So this is just a generalization of the theorem that had been given in the exercise of this section. The theorem says, let T is a transformation from vector space V to vector space W, where V and W are finite dimensional vector spaces with their respective ordered bases beta, beta dash and gamma, gamma dash. So beta, beta dash are the bases of V and gamma, gamma dash are the bases of W. So here we would be considering the change of coordinate with respect to beta, beta dash and with respect to gamma, gamma dash, both of them. So let us study what the theorem says. It says that if beta and beta dash are the ordered bases of V and gamma dash are ordered basis of W, then the matrix representation of T, what is T? What is the matrix representation of T? T is defined from V to W. So its matrix representation would be defined from the basis of V to the basis of W, that is beta dash to gamma dash. So if I am given the matrix representation of beta dash, matrix representation of T from beta dash to gamma dash, then I can obtain the matrix representation of T from beta to gamma. Matrix representation of T from beta to gamma, but I need to pre-multiply by P inverse and post-multiply by Q. Let us study further what P and Q represents. Q is the change of coordinate matrix from beta dash to beta coordinates, and P is the change of coordinates from gamma dash into gamma coordinates. Okay, so now we change when we are given two different bases and two different vectors. Okay, the following lectures would be based on the exercise that I would be covering after completing the syllabus of unit 1. So after this we will be starting the dual basis from the next lecture. So that's all for this class, and bye bye.